Hello everyone, this is the continuation of our atomic structure level, and this would be our last part in the continuation of our atomic structure. In this lecture we will learn about electronic configuration of atom, which is extremely important for our board level, NEET level and JEE level also. So electronic configuration of atoms. So first of all we will learn Aufbau principle. It's a German word. Aufbau is not a scientist, it's a German word. It means to build up, to build up, to build up. It means to build up. So, or filling up. It means to build up or filling up. So what is the Aufbau principle? In the ground state of an atom, an electron enters the orbital of lowest energy first, and subsequent electrons are fed in the order of increasing energies. That means the electron, whichever electron wants to enter in an orbital, it will enter in the lowest energy first or in the ground state first, then it will fill up accordingly. So in respect to this Aufbau principle, we have two energy level diagrams. One is for our only hydrogen, because in this case we have only one electron, and other is for multi-electron atom. This diagram is for multi-electron energy level, and from ground to earth, from down to earth, the energy will increase. See, in this diagram for hydrogen atom, 1s, 2s, 2p are in the same state. That means their energies are same. For similarly for 3s, 3p and 3d, 4s, 4p, 4d, 4f, all of them have equal energies. And we already know 4f orbital as 4f orbit has 7 orbitals. These have 5 orbitals. P has 3 orbitals, px, py, pz. D has 5 orbitals, right? Dx square minus y square, dx square, dxy, dyz, dzx and dz square. Accordingly 4f and 4s. These all, see, 4s, 4p, 4d, 4f all have equal energies. These 3s, 3p, 3d all have equal energies. 2s, 2p all have equal energy. Because why this is happening? This is happening because hydrogen have only one electron. But for other configurations, for multi-electron, we would follow this diagram. That is, first 1s, the electron will enter into first 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 4d, then 4p. How to remember? You don't have to remember this diagram. You have to remember this technique. You have to remember this technique. This is a very important technique. This is a very important technique you have to remember. This is a very important technique you have to remember. See, write down something like this: 1s, 2s, 3s, 4s, 5s, 6s, 7s, then 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, 4f, 5f. Then cross it with this: first 1s, then 2s, then 2p, 3s, then 3p, 4s, then 3d, 4p, 5s, then 4p, 5p, 6s, then 4f, 5d, 6p, 7s, then 5f, 6d, 7p. So how to write this electronic configuration? So first 1s, then 2s, then 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Go like this. You have to remember this. You don't have to remember this. You have to remember this. Otherwise, this you can't write electronic configuration. This is extremely important. Now the question is, why this is happening? For hydrogen atom, why these energies are same? For multi-electron atoms, why these energies are not same? Why there is a variation in energies? Whereas this is 2s and this is 2p. Why the energy of 2p is higher than 2s? Why the energy of 3p is higher than 3s? There are various reasons. So the first reason is nuclear charge, variation in nuclear charge. Second reason is principal energy level. Third reason is presence of electrons in the lower energy level. Let me clarify this with some explanation here, small explanation. See, we have electron, like let us say we have proton here, positive charge, and we have different orbits. In orbits we have different orbitals. So let us say this is our 1s orbital, then 2s orbital, then our 2p orbital. This something goes like this. So in 1s orbital we have 2 electron, in 2s orbital we have 2 electron, in 2p orbital we have 6 electron, because px, py, pz, in every orbital we have maximum of 2 electron. So it will have 6 electron. In 3s orbital, then again we will have 2 electron. So that means the inner orbital, see, if this is the inner orbital, let us say these are the inner orbitals and these are the outer orbitals in our case. So what this electron do, this electron will reduce the nuclear charge. This inner orbital electron will reduce the effect of nuclear charge, because what is the role of nuclear charge? It will attract the outer electrons with electrostatic force of attraction. If these electrons reduce the effect of positive charge, because these are inner orbital electrons, then we say that this effect is known as screening effect. This effect is known as screening effect. Screening effect. This is important, very important, or shielding effect, or shielding effect, or shielding effect. Very important. By screening effect or shielding effect, we will learn various properties will change in our periodic table. We will learn when we will see periodic table. But you have to understand what is screening effect. The inner orbital electrons reduce the effective nuclear charge of protons in the center. This effect is known as screening effect or shielding effect. And next point you have to remember, Z effective, that is, this thing is known as effective nuclear charge. Effective nuclear charge. Effective nuclear charge, you have to remember this. What is effective nuclear charge? Effective nuclear, see, I have just explained to you that this electron will reduce the effect of positive charge here. So for this electron, let us say for this electron, the nuclear charge is reduced by this electron, reduced. So what is the remaining effective charge? What is the remaining strength of protons here to attract the outer orbital electrons towards itself? That is known as effective nuclear charge. I am again repeating, please remember these two effects. These two effects are extremely important. So that's why if you remember the shapes of 1s orbital, it is spherical. If you remember the shapes of p orbital, it is px, py, pz. It is px, py, pz. So that means 1s orbital and 2s orbital lies closer to nucleus. So that's why these electrons will reduce the effective nuclear charge. This effect is known as screening effect. So that's why the electron will first enter into 1s, 2s, then 2p, and then d orbital. We know dxy, dyz, dzx, dx square. So that's why our electronic configuration goes like this, or energy increases from going from lower orbital to upper orbital. This is the main two reason for the variation of increasing energy. So let us continue. See, our number 2 rule is Pauli's exclusion principle. It says an orbital can accommodate maximum of 2 electrons. Let us say this is 1s orbital, so it can accommodate maximum of 2 electrons. Let us say this is px orbital, so it will have 2 electrons. Py orbital, it will have 2 electrons. So every orbital can accommodate only 2 electrons, and that is of opposite spin. So remember, 2 electrons, but 2 electrons spin should be opposite. No same spin electron can accommodate in the one orbital. So their spin is different. So one spin is shown as this, half cut, and another spin is shown as this, half cut. So our third rule is Hund's rule of maximum multiplicity. Electron pairing will not take place in orbitals of same energy or same subshell until each orbital is singly filled. That means, see, these px, py, pz orbitals have same energy. These px, py, pz have same energy. So Hund's rule says that every orbital should get 1 electron first Then you have to arrange the other electron. See, let us say we want to find out the electronic configuration of fluorine. So atomic number is 9. So 9 you can write it as, see, if you have remembered the diagram, so we have 1s, 2s, 2p, 3s, 3p, this 1s, 2s, 2p, 3s. So first of all 1s2. According to Pauli's exclusion principle, every orbital should have 2 electrons. That means you have given 2 electrons to s orbital, 1s orbital, done. Then 2s orbitals, 2s2. Then 2p. How many electrons you have remembered remained? 2 to 4, that means 5 electrons. So that means you have to fill 5 electrons. We already know that p orbital have 6 electrons and there are 3 orbitals of equal energy, px, py, pz. As it is 2p orbital, so it will have 2px, 2py, 2pz of same energy orbital. So Hans rule says that every equal energy, see, you have given 2 electron to 1s, 2 electron to 2s, then you have to fill remaining 5 electron. You have to give first 1 electron to each of the equal energy levels. So first one electron goes in px, py, pz. 3 electrons done. Then you have to come from first. So second electron, this second electron. See, calculate, you have 5 electrons in p orbital. But the filling nature should be according to Hans rule. Filling nature should be according to Hans rule, and according to Pauli's exclusion principle, in every orbital you have maximum of 2 electrons. That's how you have to fill or write the electronic configuration, something like this. Now can you solve this? Can you write down the electronic configuration of argon, scandium, chromium and copper? I am giving you 2 minutes, try yourself, after that I will solve. So I hope you have tried your best to solve this. See, scandium, atomic number is 21. See, we have already seen that the nearest noble gas configuration of argon is something like this: 1s2, 2s2, 2p6, 3s2, 3p6. Till now we have seen that this total number of electrons is 18. So whenever there is greater than 18 electrons, so you have to take the recent or nearest noble gas configuration, because you have to remember that nearest noble gas configuration is 80. So it will take the argon configuration. That means this total thing is here. You don't have to write the whole thing again and again, because nearest is 18. So argon. Then after 3p, as 3p6 is completely filled, so after 3p there will be 4s, and after that it will come 3d. So 4s2, then 3d. How many electrons remain? 1 electron. See, we have total 21. So 18 plus. So let us see, we have done with scandium. Let us see chromium and copper. These two are exceptional in this electronic configuration part. So let us see how chromium has came. See, we have already discussed that chromium is 24. So 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 and 3d 4. Count the electrons, you will have 24 electrons total. But this electronic configuration is wrong. Why this is wrong? Because see, in this configuration you can write up to 3p6 as argon, because it is the nearest noble gas configuration. After that you have to write only 4s2, 3d 4. This is also wrong. Why this is wrong? Because half filled and fully filled electronic configuration, half filled and fully filled electronic configuration has less energy. This means more stability. So it will, we already know that whatever it may be the configuration, if it has less energy, it will be more stable. It has less energy, it will be more stable. So to get the less energetic electronic configuration, how this will go, that see, this is 4s2, right? This is 4s2. Now we have 1 2 3 4 5 d orbital. So one electron will go here, one here, one here, one here, according to Hund's rule. One electron will fill first. But see, if one electron jumps from 4s2 to 3d, if one electron jumps from 4s to 3d, then see, it will have 3d5. So 3d5 is half filled, because 3d10 is fully filled, then 3d5 will be half filled. If one electron goes there, then it will have 4s1. S orbital can have maximum of 2 electrons. So if it has 4s1, that means 1 electron, then it will have also half filled. So that means in that case 4s1 and 3d5, both of them will be half filled. So if they are half filled, that means that configuration will be less energy. If that configuration is less energy, then it will be more stable. So that means our configuration would be argon 4s1, one electron will jump to d orbital, so it will have 3d5. It will have 3d5. See, both of them are half filled. So this is the correct electronic configuration of chromium. Remember this, it will come in your exam. Either chromium or copper. It will come definitely in your exam. So let us see copper. It will have 29 as proton number, atomic number or proton number. So nearest noble gas configuration is argon. Argon is 18 electron. It ends with 3p6. After that it will have 4s2. So that means 18 plus 2, 20 and 3d9. Again see, here also the same case. If one electron, this is the wrong electronic configuration. If one electron jumps from 4s to 3d, then our electronic configuration would be 4s1, 3d10. See, in this case our d orbital is fully filled, s orbital is half filled. So that means half filled, full filled has less energy, that means more stability. So copper has this electronic configuration. I think this is clear. So let us continue. To find out the electronic configuration of ions, that is for negatively charged ions and for positively charged ions. So for negatively charged ions, what you have to do, first of all write down the electronic configuration of neutral atom. This is the neutral atom configuration of sulfur. Now if we want to insert 2 electrons, that is negatively charged ions, see, our 3px orbital is filled, 3py have 1 electron and 3pz has 1 electron. So we have to insert 2 electrons extra. So it will come in 2py, 1 electron in 2py and 1 electron in 3pz, 3py and 1 electron in 3pz. So it will be 3py2, 3pz2. This is very easy. But for positively charged ions, you have to remember few things. So first point is same, that you have to write down the electronic configuration of neutral atom. Then if we want to remove 2 electrons, so you have to remember this thing. Electrons with the highest value of n are removed first. So see here, highest value of n, this is 1, 2, this is 3. So electron will remove from highest value of n. So here 3. If more than one subshell of the valence shell are occupied, see here 4s, 3d, 2p and 1s. These are value of n. So n value is 1, 2, 3, 4. So from where the electron will be removed, where the n value is largest. Here n equals to 4. So that means 2 electrons will be removed from 4s orbital. So you have to remember 2 electrons. So remove these 2 electrons. After that the remaining would be your configuration of positively charged cation. If more than one subshell of the valence shell are occupied, the one with the highest value of L loses the electron first. See, in this iron configuration, we have removed electron from the highest value of n. There are some scenarios where there will be some subshells. So in that case, the electrons will be removed where the L values, where the value of L is highest. We will see some question. Now we will moving forward to solve some questions in order to clear all the concepts we have learnt in atomic structure. So let us see some questions related to atomic structure. What is the maximum number of emission lines when the excited electron of a hydrogen atom in n equals to 6 to ground state, that is n equals to 1. So the electron jumps from n equals to 6 to n equals to 1. So we know this, remember this formula, if you want to find out the emission lines from any orbital to any orbital, then this number of emission lines would be possible, n2 minus n1 into n2 minus n1 plus 1 by 2. Here the electron is jumping from n equals to 6 to n equals to 1. So 6 minus 1 into 6 minus 1 plus 1 by 2. Calculate, you will get 15 lines. So how these 15 lines can be? See, n equals to 1, 2, 3, 4, 5, 6, right? See, n equals to 1, 2, 3, 4, 5, 6. So the electron wants to jump from n equals to 6, n equals to 6 to 1, n equals to 6 to 2, n equals to 6 to 3, n equals to 6 to 4, n equals to 1, 2, 3, 4, 5 lines. So it may have n equals to 5 to 1, 5 to 2, 5 to 3, 5 to 4 lines. Then it may have emission lines something like n equals to 4 to 1, 4 to 2, 4 to 3, 3 lines. Then it may have jump from 3 to 2 and 3 to 1. Then it may have jump from 2 to 1. So calculate, you will have 15 number of lines when the electron is excited. So n equals to 6, it drops from n equals to 6 to n equals to 1. So these are the possible combinations that you may have, that is 15 lines. But for MCQ purpose, you have to remember this formula only. 15 lines will be your answer. Next question, how many electrons in an atom may have the following quantum numbers? See, first question is n equals to 4 and ms equals to minus r. We already know this formula, that maximum number of total number of electrons is 2n square. Total number of electrons is 2n square. Here n equals to 4, so that means 2 into 4 square, that is 32 electrons are possible. For n equals to 4 orbit, 32 electrons are possible. So we already know that if 32 electrons are there, then half of them would be of one spin and another half would be of other spin. So here ms, that is spin, is given as minus half. So out of 32 electrons lying in n equals to 4 quantum numbers, half of them would be minus half and another half of them would be plus half. So our answer is 16 electron is minus half. Okay. Next is n equals to 3 and L equals to 0. This is very easy. If n equals to 3 and L equals to 0, see, we already know that if n equals to 3, then ml can have 0 to n minus 1, 0 to n minus 1. L have minus L may have minus L to. So see, here n is given as 3, so our azimuthal quantum number would be from 0 to 2, so that means L values can be 0, 1 and 2. So here the value is azimuthal quantum number value is given as L equals to 0. So 0 is for our S, 1 is for our P and 2 is for our D. So L equals to 0, that means S orbital, and quantum number n, principal quantum number is 3, so that means it would have 3s orbital. So this is the representation of 3s orbital. So S orbital maximum can have 2 electrons, so our answer would be 2 electrons. Now we will move forward to solve some other problems. Let us solve another problem. The quantum number of 6 elements are given. Arrange them in order of increasing energies if any of these combinations has or have the same energies, list them. So you have to list all the energies which are having same equal energy level. See, this is a very easy question, because for energy concerns we have to only see the values of n and l. This is the principal quantum number, right? L is our azimuthal quantum number, this is our magnetic quantum number, and this is our spin. So we have nothing to do with the spin number, because it is related to the rotation. So we will not see spin. Now for magnetic quantum numbers, we know magnetic quantum numbers defines the orientations, how it is oriented in the space. Now our main concern would be in n values and l values. We already know that if l equals to 0, then it represents s orbital. If l equals to 1, it represents p orbital. If l equals to 2, it represents d orbital, and if l equals to 3, it represents f orbital. So according to this, we can say that this combination is our 4d, because d is for l equals to 2. This combination is our 3d. This combination is our 4p. This combination is our 3d. This combination is our 3p. This combination is our 4p. Now rewind the lecture and see the energy diagram I have shown to you, that how the energy increases from bottom to up. So in that thing we can come to the conclusion that 3p, see here we have 3p, that is in the option number 5. That energy is less than 3p energy is less than 3d. Here we have 3d, here we also have 3d. That means this option number 2 and option number 4 have equal energies, because both of them are 3d, and 3p is less than 3d, we know. That means 3d energy is greater than 3p. Now this is less than 4p. Let us say we have 4p. So 4p has greater energy, and see here we have also 4p. That means 2 and 6 and 3, 6 and 3 has 4p energy. So they have equal energy but greater than 3d. And now we have 4d. Now 4d is the highest energy in the configuration. Just see the diagram. Or you can come to from this 1s, 2s, 2p, 3s. From this you can also see the variation in energies. So this would be our arrangement. So let us see another type of problem. This is extremely important type. Calculate the wavelength for the emission transition if it starts from the orbit having radius this nanometer to and ends at 211.6 picometer. Name the series to which this transition belongs and the region of the spectrum. This is extremely important. See, for nth orbit of hydrogen-like species, we know the formula 0.529 into n square by z, as z is atomic number, Armstrong. In Armstrong, this is the formula. If you want to know all the formula, please refer to my YouTube videos of in the name JE, atomic structure JE lectures. In that lecture, I have formulated all the formulas that is possible for your atomic structure. So kindly go through that. So radius of nth orbit, the formula is 0.529 n square by z Armstrong. In picometer, 1 Armstrong is 10 to the minus 10 meter and 1 picometer is minus 12 meter. So in picometer it would be 52.9 into n square by z picometer. See here R1 is given as 1.3225 nanometer. So convert it to picometer. So it would be 1322.5 picometer. It is in the 10 to the minus 12. So it will shift, the decimal will shift 3 digits in the right hand side. So nanometer to picometer. So this R1 is the radius of Earth orbit. So this R1, this thing should be equal to this thing. So for n, for here we are writing as n1. R2 is given as 211.6 picometer. So it will be n2 square. Divide R1 and R2. cancel, Z cancel out, 52.9, all these are cancelled out, and this division will get you will get it as 6.25. So n1 square divided by n2 square is 6.25. So after taking square root, you will get n1 by n2 equals to 2.5. Now here comes the logic. You got the orbit number n1 by m2 equals to 2.5. So what type of transition that is possible? That means what value you can take so that the ratio would be 2.5. See, if we take n2 as 2 and n1 is 5, so 5 by 2, that must be 2.5. So here if the value is 2.5, then our transition should be from n1 5 to n1 n2 2 to 5 is our transition. And this transition, see, it ends at n2 equals to 2. That means it is the Balmer series, right? It is the Balmer series. If it is Balmer series, then it should be visible region. Balmer series corresponds to visible region. We already know that. Now here it is given that calculate the wavelength. Name the series to which the transition belongs and the region of the spectrum, and the main question is calculate the wavelength. These two things we have got, Balmer series and visible region. Now wavelength. Now we know wave number as 1.097 into 10 to the power 7 per meter into 1 by n1 square minus 1 by n2 square. So here 1 by n2 square minus 1 by n1 square. So 1 by n2 square is 1 by 2 square minus 1 by 5 square. Calculate these values, and we know that lambda nu bar is wave number is 1 by lambda. So lambda is 1 by nu bar. So lambda is 1 by nu bar. After calculating this value, you will get this value. So 1 by nu bar. So lambda would be 1 by nu bar, that means 1 by this thing. After calculating, you will get this thing 10 to the power minus 9, 434 into 10 to the power minus 9 meter. So that is 434 picometer. And this is the obvious region that it lies in visible region. This type of problem is extremely important for your NEET and JEE also. Please refer to this type of problem. By this we have ended our lecture. I hope you are enjoying it. Please like, subscribe and share it for 200 likes. If I got 200 likes, I will solve at least 20 problems related to atomic structure. All the best. Have a good day.